So in determining whether a series will diverge or converge, there are several tests that we'll talk about. And here we'll focus on the divergence and integral tests. So let's start with the divergence test. If the series converges, and again, this is assumed to be an infinite series, okay? We just don't write the where case starts, but this is going to infinity. If this converges, then the limit of the terms goes to 0. The contrapositive of that is to say if the limit of the terms does not go to 0, then the series diverges, okay? And here's a basic sketch of the proof of subtracting the partial sums, sk and sk minus 1, well, that's equal to ak, and taking the limit, you should get 0, okay? So here's a very important remark, okay? The divergence test cannot be used to determine that a series converges, okay? It can't tell you if a series converges. It can only tell you if a series diverges, okay? And so if you do find that this is true, that the limit of the terms goes to 0, you cannot conclude that the series will converge, okay? You cannot do that. All that it tells you is that if the series converge, then this has to be true, okay? It doesn't say if this is true, then the previous has to be true as well. No, it does not say that, okay? The contrapositive, which is the equivalent statement, is to say that if the terms do not go to 0, then you know the series will diverge. So determine whether the following series diverge or state the divergence test is inconclusive. So A, let's take that limit. Is it 0? No, the series diverges by the divergence test. What about B? Okay. B there, we will break up the terms. This term goes to 0, but that term does not. So the series diverges. What about this guy? Okay, well, the limit as k goes to infinity of 1 over k is 0. Does that mean that this converges? Absolutely not. In fact, it doesn't converge, as we'll see with the integral test. This does not converge even though its terms go to 0. So here the divergence test is inconclusive because the divergence test cannot tell you that a series converges, only that it diverges. What about this over here? Well, it turns out that this series actually converges, but taking the limit we get 0. And can we conclude from the divergence test that the series will converge? Again, no, we cannot. So both of these have terms that go to 0. Only this will actually converge. But in both cases, the divergence test says nothing, okay? The divergence test is inconclusive. All right, so let's talk about the integral test. So it's important to focus on the hypotheses here. Suppose f is continuous, positive, and decreasing function, okay? For x is greater than or equal to 1. And let ak be equal to fk, okay? So this is a function. It's a real function where at the integer values you could express your sequence, okay? Then the sum and this integral here, okay, which both are going to infinity, they either both converge or both diverge, okay? So if one of these converges, the other converges. If one of this diverges, the other one diverges, okay? In the case of convergence, the value of the integral is not equal to the value of the series. So they're not equal. They just either both converge or diverge. It doesn't mean that they're equal, okay? And here we have a basic sketch of the proof that you could basically bound this integral using left and right sums, Riemann sums, okay? And from there, you could show that the partial. So if you assume the integral converges, then you could show that the partial sum is bounded and increasing, and hence the infinite series will converge. On the other hand, if you have that the infinite series converges, then the sequence here is increasing bound and hence converges. And it's important that these were positive and decreasing for this proof to work out, okay? So let's go back to that harmonic. The harmonic series is this, okay, this 1 over k. It's called the harmonic series. This is how it looks when you express out the terms. It diverges. Even though the limit as k goes to infinity of 1 over k is 0. So even though its terms tend to 0, it diverges. Well, take a look at the integral. This could be expressed with the function 1 over x. We just call it 1 over k. 1 over x or 1 over k is decreasing, it's positive, and it's continuous. And so we have fulfilled all of the hypotheses in the integral test. Okay, the hypotheses are the assumptions. And so integrating from 1 to infinity is infinity, and so the integral diverges, and so must the series, okay? So let's take a look at another example here. Determine whether the following series converge, okay? Well, for A, the function, the equivalent function of this k over k squared plus 1, for the real numbers is x over x squared plus 1. And of course, it equals the sequence at the integers, okay? At the integers k from 1 to infinity. Well, this is continuous and positive for x is greater than or equal to 1, which is the domain that we're interested in. We need to check that it decreases, okay? Again, because of the hypotheses there. That's super important. So we do need to check that it decreases. And we take the derivative, and we notice that this is strictly less than 0 when x is strictly greater than 1. And so f of x is decreasing for x is strictly greater than 1, okay? And we'll then integrate this function. We'll take the improper integral. Okay, we'll take the limit as b goes to infinity of that, and we get infinity, so it diverges. And by the integral test, then the series also diverges. Okay, and again, notice that as the limit as k goes to infinity of these terms, it does go to 0. Okay, for b, again, these terms tend to 0, but that doesn't tell us about about the convergence. So we start at k equals 3, and that's fine. The theorem had us at k equals 1, but only the end behavior is what matters. Okay, so even if we find that a function decreases after a certain x, then that's fine. So here's f of x. It's clear that it's continuous, positive, and it's clear that it's decreasing after x is greater than 3. I mean, 2 times 3 is 6 minus 5. That's just only going to, 2x is going to keep increasing, and so that you could see that it is decreasing. It's intuitive to see that. And so doing this integral from 3 to infinity, we integrate, we get a divergence. So guess what? The series also diverges. The integral diverges, the series diverges when we fulfill the hypotheses. Well, what about this guy? Okay, again, k goes to 0. Divergence test is inconclusive. These terms go to 0 when k goes to infinity. So here's the function that we could use that will give us that will equal the terms when we plug in integers. It's positive, it's continuous, and it's intuitively decreasing there for x is greater than or equal to 0. And so we integrate this, we get arctan. When we take the limit as b goes to infinity, okay, we get pi over 4 for what that improper integral is. And so the integral converges, and since the integral converges, the infinite series also converges. Okay, does that mean that this equals pi over 4? Absolutely not. The improper integral equals pi over 4, but not the series. Okay, so you might have noticed that 1 over k will diverge, and 1 over k squared will converge, and so it's important to sort of find that dividing line. And so we have this theorem, and these are called the P series. When you have 1 over Kp, these are called the P series. This series will converge whenever P is strictly greater than 1 and diverge for P less than or equal to 1. Okay, so if P was equal to 1/2, 1 over square root K, well, you get divergence. But if P was 1.0001, then it will converge. Okay. And this is the case due to the integral test. So if you take the integral of these terms, you'll get the exact same behavior there for convergence of the improper integral. So let's determine whether the following series will converge or diverge using this P series. Well, for A, k to the -3, well, that's just the same as 1 over k cubed. And so P equals 3, that's strictly greater than 1. And by the theorem above, the series converges. What about this over here? Well, taking the fourth root is the same as, taking the power to 1 over 4. And so you get k cubed raised to the power 1 over 4. That's k to the 3/4. 3/4 is less than or equal to 1, and so the series diverges by the P series test. And what about this over here? Well, we're going to re-index. We're going to start from, just to frame it in the language of the P series, instead of starting at 4, so if you put in 4, you get 4 minus 1, that's 3. You could just start at 3, and that's the exact same sum, okay? But if you change from k minus 1 to k. And again, we could have done this by using a different dummy variable like j is equal to k minus 1. And then sum from j equals 3 to infinity, but those are just dummy variables. So it's all right that we called it k again. But we're starting at 3, and here 1 over k squared, that means p is equal to 2, which is strictly greater than 1. The series, the series converges. Okay? And all right here, because finite amount of terms cannot change convergence, that's because this theorem tells us that the convergence occurs from k equals 1. Well, adding the first, for k equals 1 and k equals 2 of this, that's not going to change. That's just a finite amount of terms, so it cannot change the convergence. I mean, even if we added another trillion terms to this, as long as they're finite, it's not going to change the convergence. So let's conclude with talking about how to estimate the infinite series. So I emphasized a bunch here that the improper integral is not equal to the infinite series, okay? But maybe we could use integration to give us some bounds on or estimation of the series. So here we define what's called the remainder, okay? Here's our infinite series, and we're going to subtract out the first n terms, okay? So if S is the sum of the infinite series, okay, Sn is the partial sum of the first n terms. And so what that is, the remainder is basically the remaining terms outside of that partial sum. So you start from n plus 1, and then you go to n plus 2, n plus 3, and on to infinity. Okay, that's the remainder. And here's a theorem. Let f be a continuous positive decreasing function for x is greater than or equal to 1. And let ak equal fk. Okay, so this function at the integers, at the positive integers, gives us our sequence. For k is equal to 1, 2, and on and on. Okay, let S be the infinite series, okay, the sum of the infinite series. Let it be a convergent series, and let Sn equal the partial sum, okay, from k equals 1 to n, the nth partial sum, be the sum of the first n terms of the series. The remainder, okay, which we have above, it satisfies this relation, okay. The remainder is going to be strictly less than n to infinity of f of x. Furthermore, the exact value of the series is bounded as follows. So we actually get a lower bound, Sn plus the integral from n plus 1 to infinity, is strictly less than the actual sum of the infinite series and is less than this upper bound on the sum of the infinite series. Okay, so we have an upper bound and we have a lower bound. Okay, and the difference here is that you're starting from n. Here it's n plus 1. Okay, and again, it's important for this to be, for the function to be continuous, positive, and decreasing. So let's look at an example. How many terms of the series must be summed to obtain an approximation that is within 10 to the minus 3 of the exact value of the series? Well, if the remainder is smaller than 10 to the minus 3, then we're going to be within 10 to the minus 3 of the exact value of the remainder is what's left. Okay, it's what we have to add to get the total sum. Okay, so here we basically want the remainder to be less than 10 to the minus 3. Well, we have this theorem that tells us the remainder is less than that integral. If we take that integral, we'll get 1 over n. So we know that the remainder is less than 1 over n, and now we have a bound with n. So if we need Rn to be less than 10 to the minus 3, and we know that Rn is less than 1 to the n, so if we make 1 over n less than 10 to the minus 3, then we fulfilled this condition. And so taking the reciprocal of both sides, we flip the inequality and we get n is strictly greater than 10 to the power of 3. Okay, so if you sum more than 1,000 terms, then you're guaranteed that you're within 10 to the minus 3 of the exact value of the series. Notice we don't need to know the exact value of the series. Okay, we don't need to know that. We already have a bound on the remainder, and so there's no need to know the exact series. So we could just sum the 1,000 terms and say, well, we're within 10 to the minus 3. So you'll sum the first 1,000 terms and you'll write, or the 1,001 terms and you'll write plus or minus 10 to the minus 3. B, find an approximation for the series using 50 terms of the series if S50 is approximately equal to this. Well, we have a lower bound. Here's the lower bound, Sn plus the integral from n plus 1, right? And so we get Sn plus 1 over n plus 1. We have an upper bound using this formula, and we have 1 over n there. And so we know that S is bounded by the upper bound and lower bound. And we're doing this for 1 over k squared, right? And so S50 plus, we just plug in 50 wherever we see an n. And we get, because we already know what S50 is, we could add that to 1 over 51 and we get this. And we add it to 1 over 50 and we get that. And so S is between these values. Okay, and so we have approximate location of what that sum is. And in fact, one thing that you might have thought to do is just to take the average of the lower bound and upper bound and hope that you're there. And so here's a way to estimate S. Look, this is approximate, it's not exact, but that's one method there for approximating the infinite series, estimating its value and getting bounds on the error if you're taking a certain amount of terms.